Hello everyone, welcome back to Advent of Code. It's 2020 day 14 today. Let's get started. Day 14, docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange bitmask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program can either update the bitmask or write a value to memory. Values and memory addresses are both 36-bit unsigned integers. For example, ignoring bitmasks, an instruction like mem of 8 equals 11 will write the value 11 to memory address 8. The bitmask is always given as a string of 36 bits, written with the most significant bit on the left and the least significant bit on the right. The current bitmask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. So it's sort of like a combination of two masks in a way, right? One mask that's like where to apply zeros, and another it's where to apply ones. It's not. I guess it's actually. Well, whatever. Doesn't matter. It's a bit mask where you don't have bits. You have like optional bits. The program starts by specifying a bit mask. The mask it specifies will overwrite 2 bits in every written value. So in this case, you overwrite the 2's bit and the 64's bit. Then it attempts to You need the sum of all values left in memory after the initialization program completes. And the program starts initialized to 0 everywhere. Okay. Well, let's go like at least start by looking at our input. And see what's up with all that. Okay, so it is allowed to overwrite the mask many times, but it doesn't do anything besides like setting the mask and fiddling with memory. Okay. So this is a pretty simple computer language to implement. And also pretty easy to parse, I imagine. Like, we could do this with regex applicative. I don't know if it's really necessary. Yeah, well, I mean, I think we might as well. It'll definitely be longer than writing it out with like unsafe operations, but it'll not be terribly unpleasant, and the end result will be nice. Okay, so let's import text regex applicative, import data int map. What? Oh, because this REPL has been opened for too long? That doesn't seem right. What? I'll quit Emacs, I guess, but should have done this in the other. Whatever. I'll just use Emacs in this one instead. Actually, it's like taking forever to build. Why? Shouldn't this all be in my cache? I don't totally understand how stack works, but I didn't think there was any way to implicitly say, oh, to like get a new version without asking for something. Huh. That's even importing comonad. Who knows what? Oh, I mean, transformers probably needs it. That makes sense. Sort of. I mean, like... Oh my god. Well, whatever. If it can't handle text regex applicative yet, then whatever, we'll get it later. Now it can. See, I don't know. Oh, I mean, no. No, I want you to go away so I can just type shit. Hello? I hit restart? Like, it's just really mad that I'm doing this while building, apparently. I want to not... did that do it? Now I seem to be allowed to move stuff around, and I've just told it to cancel. I aborted the prompt, I think. Okay, so we need some data types here. Oh, it went off anyway. Data. This is the dumbest. I don't even know why it needs to build anything. All right, let's go look at the problem again a bit. So one question to ask is, like, how exactly do we want to represent the bit masks? We could just represent them as a sequence of 26 things, right? And never actually treat them as numbers at all. But we need a way to convert them to numbers in the end anyway, in order to sum them up at the end. So we could say, all right, well, let's always represent them as numbers. But then it's like kind of awkward. We need a way to convert them to their component parts to combine them with each other, right? So we seem to need a way to convert... Well... Like, we don't have to use the same storage format for the mask and for the numbers, right? We can store the mask in a fancy way, and then just compute from it a function that is applied to numbers. And then do everything else in the number domain. That seems pretty reasonable, right? Okay. Has Haskell finished? It has, okay. Yes, restart. Does that work? I think it worked. So actually what I want is like a data instruction, say, is either a write of address value, which are both ints, or a mask, set mask of mask, not mark. And I would like I'm not sure what type I want mask to be. The obvious thing is a sequence of 26 trits, or whatever you call ternary bits, right? I think trits is the term. It's sort of tempting, though, to have it just be a function from int to int and compute what that function is when we parse the mask. I think that's like premature optimization, though, and leads to a poor domain model, because we're assuming we understand what the mask will do every time in the future. But like, who knows? Part 2 might say, understand the mask differently. And I'll be like, oh no, I baked in my representation of the mask, and now I just have this function. So I think that the mask should really be a sequence of trits or something. So let's define that. which is just pass or set or clear. Data mask new type. Now, technically this is incorrect, right? Because it's possible to set a mask that is not 26 bits long. And we should do, oh, hang on. We should do some validation, or like ideally, like, the type that best describes what this is would be mask of trit with 26 fields, right? But that's obviously very inconvenient to work with. So instead, I think I will define a function that creates a mask and like produce some sort of error if you don't have exactly 26 trits. And then if this were a library, someone else could use our mask and like they could rely on masks to always have 26 trits because we wouldn't let them we wouldn't let them create an illegal mask. Since we only have ourselves, so like that safety is not really as interesting or as guaranteed because we have permission to write whatever nonsense we want. But as long as we always have the discipline to use the make mask smart constructor, it would be safe. So what I think I want is make, I was gonna have make mask produce a maybe, but then it's like a little bit unpleasant when I'm parsing them, I think. I mean, my parser is just going to say there should be 26 of them, right? So it's sort of like impossible to ever create a bad mask to begin with, but okay, whatever. And we're getting them in highest first order, right? So the interesting thing to do is to write a function here called, let's say, apply, is a function from mask to function of int to int. And we can even write the unnecessary parentheses here to sort of clarify we wish to think of masks as functions from int to int. And how exactly do we write this? Mask, oops, apply mask trits equals go trits, probably? Where go of empty, like this is some kind of fold, right? Like I kind of want to view the trits in reverse order. It sort of seems easier. I don't know. I mean, maybe I should just say go trits of 26 or something. Or 25, I guess. The power of 2 that we should apply the current trit to. Undefined, let's say, and go of so the idea here is we expect no, hang on. This is actually we expect 0 to happen, don't we, at some point? I don't know, this whole thing's stupid. Like, why don't we just have the mask apply backwards? And then we can just do the doubling inside of Go, or the counting. We would have to be passing a 0 anyway, I think, right? So seems fine, but because we're going to be applying this Go function 26 times, which means it should be 0 when there's one thing left in the list, right? Oh, n, thank you. And I think what we need is that we need somewhere first a function from trit and position to function from int to int? No, just trit to yeah, I guess. What do you call such a thing? Interpret? I don't know. These names suck. It's function from trit and int to int to int. Interpret of pass n equals n. Interpret of set. See, here's the thing. I think I want to do it in this way. No, because I don't know, this is stupid. Put it back. Set of power and n equals, oh, it's in data bits, right? Haskell data bits. Dot and dot or dot complement and shift. Shift L and Shift R. God, what is wrong with the styling on this page? Do I want this one? Oh, this looks pretty. Looks weird, very different from all the other Haskell stuff I've seen, but okay, we have and or complement shift. Oh, bit, really? Oh, we have set bit. We have set bit and clear bit. I had no idea. That's nice. I don't have to implement all this shit with and or. Well, that's great then. Because now I can actually do what I wanted to do. Use const identity equals set bit. Although set bit takes the n seconds. I think for both of these we actually want to flip it. Interpret clear e equals flip clear bit. Let me just make sure I understand what these do. Bit of I, the ith bit, doesn't actually tell me what that is, but I hope they mean, well, let's just import and find out, shall we? Import data bits, set bit, clear bit. What's wrong here? Aren't we returning? We have a flip is applied to too few arguments. Yeah, I mean, I get that, I guess. But isn't setBit a function of 2 arguments that returns an int? Which is the same as an int to int to int? Yeah. Int CC now. So if I said like this applied to, I don't know, 3 and 7, I get 15. That's probably right. Setting the 3rd bit in the number 7. Yeah, that would be. Wait, what is that? Is that right? Yeah, that added another 1 at the top. Okay. So why are these? What? These types look right to me. Const is applied to too few arguments. All 3 of them agree that I have the wrong number of arguments. Type of identity is A to A. What is the type then of const identity? B to A to A. Oh, all of these P's make no sense now. Okay, so if we said then interpret set of the bit numbered at position 4, which is 2 to the 4th, which is 16, in 19, we should just still get 19, right? Yeah. Now if I said to do it in 3, we should get 19. Cool. And if I said to clear 4 and 19, we should get 3? Looks good. All right. So that's easy. I'm wondering if this whole stupid Go thing might just be like some map-accum-L maybe again? I mean, not really. Go TTs I n equals. We're going to apply we're going to interpret the T and I of n, and then call go on that again. Go T's pred I, like so. Okay. So is this correct? Apply, it's kind of awkward that I can't work with masks smaller than 26 in this way, huh? It would be really nice if we just worked with an arbitrarily sized mask and stored the mask in reverse, but I'm a little wary of doing that. Oh, maybe what I could do instead is zip the trits with a list from 25 down to 0, acquiring a list of functions, and compose them all. Then it would be easy to work with masks of any size. I like that better. Let's write it with a let first. Let f's equal zip with interpret trits and 25, 24 down to 0. Now we need to fold left or right. It doesn't really matter, right? So I guess we might as well fold strict left. Fold L, lambda, the accumulator's on the left, f x. Oh, is this just dollar actually? I was calling f of x? Okay. Starting with I can have the n be implicit, right? Flip this, so it now wants its list argument next, like so. No. The accumulator is on the left. Oh, not trits, but f's. Thank you. Yes. Okay, so if I now said to, let's say, apply a mask of set pass clear to, I don't know, 9? What should I get if this is correct? I should clear the bottom bit, yielding 8, and then set the 4's bit, which is currently not set, yielding 12. Not very correct. Oh, but that's because... Right. Because I said to start... I'm still only handling ones that are full-sized. So if I were to say... replicate 23 of pass plus this, I would get 12. Okay, so this looks like it's correct. Great. Now, our input will be a list of instructions. Now we need to parse this. Prepare is traverse parse lines, where parse equals instruction. And we'll just write this little regex. It'll be lovely. Instruction equals setMask or setMem, write mem, let's say. SetMask is easy. SetMask is string mask equals, which we ignore, and then it is I'm going to just use applicative do. I never know how the operators go here. So let's just ignore this. And trits comes from replicate m26 of trit. We'll need to import replicate m, I assume. Where's replicate m exactly? It seems like it should be in control monad, but also it's like works on applicatives. Okay, it is in control monad. And then we will just say mask of, well, pure of mask trits. Is that right? That seems fine. Trit equals one of three things, right? It's sim1 in that case. Oh, I see. I should write the thing over here. Probably with parentheses as well. Set on sim1 or clear on sim0, or else pass when given sim x. Write mem is pretty easy as well. Let's just write a do for starters here. And we're looking for string mem. Address is an int. String close brace space equals space. Value is an int. And then we will say pure write of address value. Seems about right. Int is read of many psim is digit. We need is digit from data char. There you go. Not mask, pure set mask of mask of trits. What are you upset about here? Oh, I don't have from maybe. Data maybe. What are you upset about here? Use map. Oh yeah, sure. I'd rather not if that's the same. It's all the same to you. Okay, and then we can say let's see if we can parse the example input correctly. Where the example that they give us is this. prepare. Now, I guess we don't have show instances, so this won't actually work. It's an input. Yeah. Well, I mean, I think that means it worked. But let's just be doubly certain by actually adding some show instances, shall we? Nope. All right, that's cool. Well, we know it failed. So let's say we just wanted to parse this. That works. And if we were to give it the same line twice, that also works. So I assume the problem is with this mask, right? Yeah, that doesn't parse. Why? Set mask. They are 1, 0, and X, right? Yeah. What if instead of replicate M, I said many? Maybe there's a number other than 26, and I'm confused for some reason. Yes. That doesn't seem right. Oh! There are 36, and I just misremembered. Okay. Cool. So this all parses. Well, let's encode that important information in a file somewhere before I forget it, because as you can see, it's going to be messed up here. Mask size is an int. Mask size is 36. See, as soon as I put a 36 in here, I should have, or 25, I should have like felt bad. So mask size -1, mask size -2, and so on down to 0. And here, and now, if we parse the original input, it should be correct, yeah? Yes, there we go. And it's setting 8 to 11. Okay, cool. So we can just interpret this now, right? And I suppose we... Well, I don't know. We might want to land the case in a moment, actually. I guess we may as well write a function called run, and like, might be useful to share between part 1 and part 2. We'll see. How did this get all the way down here? Run takes a, I guess, an input and produces. I just know we're gonna have to rewrite run for part 2, and I don't know exactly what to factor out of it yet. God, these 2 flips are looking kind of stupid. Oh well. It takes an input and produces. Well, I mean, in order to implement run, we kind of need something simpler, which is called step, right? Which takes a computer and an instruction and gives back a computer, probably. And we just have to define a computer as well. Data computer is a computer of what? Like, actually, I guess it's just two things, right? A mask and an int map of int. Step mask mem equals, well, I don't want lambda case, it turns out, because the first thing I'm going to do is write case. Oh, this is wrong. No, maybe I did want it. Computer of mask and mem equals lambda case set mask m, and call it mask prime. Don't need parents there. To computer mask prime mem. And the other kind of instruction is write adder val to be computer mask prime mask of m dot insert mem. No. What order do you want this stuff in? The key, which is adder. And then what we're writing, which is apply mask to val over mem, right? And that's it. So part one then is, it's like a sum. Get out of here. What? I just want to look at my program. Composed with fold L, I guess. Step of computer. How does the mask get initialized? I think it doesn't matter because the program begins by specifying a bit mask. We'll just say like empty. I guess that's already breaking our guarantee that a mask always has 36 trits in it, huh? Replicate mask size of pass, just in case. We'll set it to a bunch of x's. And m empty, I guess. This should be a mask. So fold L step what is the type of fold L? Oh, the type, please, of it, not whatever F means. Yeah, so it takes the accumulator argument first, which is what I've written. M dot vals? No, elms. I don't think it matters. It should be the same problem because maps are foldable anyway. Oh, of course. Well, now I get a much better error message because I said I expected a map. Just saying, oh, I expect my thing to be foldable, and it's like, geez, I don't know what you mean. The point is that I have to here extract the computer's memory, right? some mem, where some mem of computer mem equals sum of mem. All right. Let's see if it runs. Will it blend, etc., etc.? It's a large number. It seems like very large, but I guess there must have been a high bit set somewhere in there, and there are 36 bits, so okay, fair enough. Values left in memory. Okay. That's the right answer. Cool. Day 14, part 1. Let's have a look at part 2. For some reason, the Seaport's computer system still can't communicate with your Fairy's docking program. It must be using version 2 of the decoder chip. A version 2 decoder chip doesn't modify the values being written at all. Instead, it acts as a memory address decoder. Immediately before values written to memory, each bit in the bit mask modifies the corresponding bit on the destination memory address in the following way. Oh! They changed how you interpret trits as well. Ugh, disaster. Okay, so 0 remains unchanged. 1 is set to 1. X means floating? Oh no. Wow. In practice, this means the floating bit will take on all possible values, possibly causing many memory addresses to be written all at once. Oh, that's exciting. When this program goes to write memory address 42, it first applies this bit mask. After applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. 4 bits are overwritten, 3 of which are different? What does that mean? Different? I don't know, whatever. Four bits are overwritten. What does that even... I don't understand. I guess they're just saying this was the original address, and this is the new address. We made changes to these 4 addresses, and in 3 of them it changed, but here it actually stayed the same. Okay. And 2 of them are floating, meaning that we actually end up writing this value to 4 different addresses. It first applies the bit mask. So bad try to 26 with a... Oh, that's... Okay, then it's saying the next step is to write to 26. Okay, so first it wrote to 42, and it happened to get to 26 instead of 42? Why? Oh, because we unset a couple bits, I guess. Okay. Then it decided to write to 26. Okay. All right, that's exciting. So, the good news is all of our parsing can remain unchanged, which is not surprising. We represented the domain in a sufficiently generic way. Or rather, we captured all the information that the program gave us, the input gave us, and only interpreted it later. So we have to change how we interpret it, but not how we read it. And it seems like interpret, apply, and step are like, they kind of all need to change, right? And it sure is tempting to just like blow up the input into a sequence of bits and then zip that with the trits, right? Is that like... Sadly, data.bits does not give you a way to take an input and blow it up into a number of bits. It's not hard to write yourself, of course. But like, we can no longer understand the value that we're working with as a number at all. Right? The value we're writing, yes, fine. But the memory address that we're writing to is not just like a bit mask applied to a number yielding a number. It's like a number applied to a bit mask yielding a list of numbers, right? Actually, isn't that exactly what fold M does? Yeah, I can just do something very similar to apply, but use fold M instead of fold L. And what is that going to do exactly? Well, good question. Not the right thing. Is it? Well, so we'll be able to zip powers with trits. Okay, it'll have to be a little bit... We'll actually want like zip with 3, I guess. Huh. Where we zip a power and the input int and also the trit all together, right? So let's say apply floating is a function from mask to list of int. No, mask and int to list of int, right? And apply floating. Yeah, it's a little bit awkward to get out the... Well, no, it's easy to get the bits because I'll have the power just lying there. I'm zipping with... Okay. Apply floating of mask trits and n equals... Now let's start writing some lets. Let powers equal... Actually, you know what? This should be... Okay. So let's not do that anymore. Let well, here's the thing. It's kind of just mapping sum over Alright, let's leave that for now. Let bits, I guess, equal zip with 3. And this wants the function first, yes. I'm gonna need to sequence at some point. That's what it is. Or maybe I want traverse, I don't know. Zip with 3, flow, interpret floating, and then oh, no, I have the n. I don't need to zip with 3. I can just zip with 2 and have n lying around here, and I'll just do the modulus inside of interpret floating. Trits and what did I call it? Powers? Powers. Okay. And interpret floating of t and p equals case t of well, you know, since these aren't set and clear and pass anymore, I should probably just call them 1 and 0 and x. So let's just make that change now. Pass to x. Set 1 and clear to 0. Okay. Case t of, so if it's a 0, then there's only one possible result, which is the bit, and we'll define the bit in a moment. 1 is just 1. Not 1. Let me just confirm what this does here. 0 remains unchanged. 1 overwrites that bit with 1. Okay. So if it's 0, we have bit. If it's 1, then we have what's the function in data bit that I wanted? It's actually called bit, so maybe I shouldn't call this one bit. Bit of p, I guess? And if it's x, it's more exciting. It's both at once 0 and bit of p. Oh, okay, we're only using b once apparently. So I can just say, actually what I need to extract out is bit of p, right? All 3 of these need to share this. Where what do I call bit of p? I don't know. Index is like obviously wrong, but index. And so if it's 0, this is the only time we care about n, right? So it's in data bits. We want there's test bit, I guess. It's not quite what I want. Case test bit. Oh, actually, you know what I can do? I can say test bit. What arguments to, it takes its order the number first, right? And then the offset. Yeah. NP of false, 0. Oh my god, what's wrong with my indentation? True, index, so it's all looking kind of stupid. So index actually could just be called B, really, right? Actually, let's call it on. I suspect the reason it's indenting weird is because Haskell wishes I would indent like this. I don't know. Now, really, this is just like a call to the maybe function, I guess, but like this kind of sucks. I think I like test bit anyway. No, not maybe, bool. Bool 0 on of test bit p. Okay, fine, you got me. Bool 0 on test bit and p. Maybe just import from bit test bit we need as well. It's all failing to parse because I haven't closed this let, which is fine. I'm not done with it. And now we have a list of lists of ways that we could interpret this number. And if I sequence it, I would just get a single list, which is not at all what I want. Right? Yeah, I have a list because I zipped the trits with this function. And this function returns a list. So I have a list of lists. And I want a way to like choose from each list, right? Something feels wrong here. I don't have the list nesting quite right somehow, I think. Do I in fact have a list of lists? I must. Is that what I want? I think so. But what do I do with it? Like I'm looking for what I have. Let's say this. I have a list of int, right? Do I just want to map some? Is that all? It seems like it should be fancier. Yeah. No. No, I don't want that at all. Do I want? I think I do want to sequence this, right? It makes sense. I have a list of choices to make non-deterministically, and I want to. I mean, you can think of lists as non-determinism, which I think is a cool way to think of them, right? We could say, oh, this is just a list of things, but another way to think of it is, you know, what if our program could just choose arbitrarily and like choose, let's say, correctly each time? You can represent a list and say, oh, here's all the choices you could make, and like choose two things non-deterministically is to choose the first one and then like choose the second one, right? And so sequence does that. So I think if I sequence this, this is what bothers me. What do you actually get if you sequence like a list of ints? I think I have the right idea. So let's say I had, you know, we can have 5, like it's got to be 5, and like, well, okay, it should probably be a power 2, right? and 4. It's got to be 4, and there's a 0 here. That one's got to be 0, and this one is either 8 or 0, and this one is either 6. Yeah, let's just leave it at that. Yeah, so when you sequence it, you get exactly what I thought. They all start with 2, 4 and have a 0, and there's either an 8 or a 0 there, right? So if we then say map sum over this, we get, oh yeah, it adds up to either 14 or 6. So that is what I wanted. In map sum sequence bits. What's going on here? Why is there a 1? Oh, this is changing set mask, and it somehow it applied there, but nowhere else. I'm a little confused. Because I started here, and it applied only below this line. I get it now. Okay, so if we then, yeah, apply floating seems probably fine. Let's test it though, right? I had some previous calls to apply, right? So it apply this, and it yielded, I'm already forgetting. We don't, they're not called pass and, oh, these are now X's. So we'll make these all zeros instead. And this will be set, and this will be X, and this will be, not X, it's 1, 0. So what should this be? Well, we're starting with a 9, and we're saying you should definitely turn off the low bit, right? And you should turn on the 4's bit, and the 2's bit you should allow to toggle. So this should be like 8. Oh, hang on. Well, first of all, this one is still, hello? Is it not called x1 and 0? Oh, my function, my program doesn't compile, so I can't run any of that. There we go. Set mask. That's what's wrong. I knew it had to be wrong somewhere else. So now this yields 4,105? Oh, because I was wrong about how many of these are. 33. Yields 4. But if we apply floating, it should yield either 4 or 6? 13 or 15. Well, that's just not correct at all. Is it? Oh, wait. Yes, because this 0 now no longer means to drop off the top bit. It means to leave it alone. So we actually, I was off by, what? This can't be right. How can it be? Oh, 0 doesn't mean to turn it off. It means to leave it alone. Right. So we say leave alone the bottom bit. It stays 1. Then the 2's bit is either 2 or 0. The 1's bit, or the 4's bit, we turn on, and it was previously off. So we have a 1 and a 4 and an 8 from the input. That's 13, and we flip on a 2 optionally, yielding 13 and 15. Okay, cool. So this is actually correct. One minute, I'm gonna go fiddle with my music, which just started playing weird stuff again. We'll just listen to this. Yes, so we have apply floating. And we could write a new step, but there's not really anything to reuse there. I mean, I don't know. I guess set mask could be the same, right? But the write has to change dramatically, so I don't mind rewriting it. We'll just say step floating is this. Computer mask mem equal lambda case set mask prime computer mask prime mem write adder val computer mask and all right, how do you Haskell data map, data int map, let's say. Data int map, we could use data int map strict, I guess. Right, and I want to like insert, I guess, or maybe combine. So insert I already have, that's fine. How do you combine? Here it is. So union creates the, I don't want that, really. Union with. Okay, I don't want that. I guess I just need to fold my own. I mean, I could just use unions, I guess. Or just a single union and pass the new thing I want to write once and use from list. I guess that wouldn't be so bad. Mask M union of, it's left biased, so we're putting in the new one first. Writes and then the old memory as the default. Where writes equal m dot from list of a val, where val comes, where adder a comes from apply floating on the mask and the adder. It type checks. I'm willing to believe it could be correct. And this is going to be very similar as well, huh? Okay, so we'll implement run is a function from one of these. Seems like this could maybe use a name, but takes one of these and it yields a function from input to int. Run f equals basically all of this, but we just say f instead of step, and part 1 is run step, part 2 is run step floating. Okay, I mean, whoops. Let's see what happens. First of all, do we still get the same number for the first one? One imagines, but that's worth checking. Yeah, I mean, it looks about the same, right? 587 ends with a 5. This, I'm a little surprised this number is not much larger. Actually, maybe it is. How many digits is this? 3, 6, 9, 12, 13. 3, 6, 9, 12. It's actually a smaller number. Well, it certainly doesn't prove that it's wrong. It's a little suspicious. That's the right answer. Cool. Well, let's... Did I do anything cool today? Well, we'll just commit this. Day 14, part 2. Oh, here. Sorry. You guys can see what we did. We had to add bit and test bit, and we imported data bool, although it's not really clear that it was worth doing. We renamed trit. We extracted out the powers we might need because I ended up needing them in both totally different application functions. We renamed pass, set, and clear to x1 and 0, which was arguably, I don't know. It's unclear whether that's better or worse. Like, obviously, given that we know what part 2 is, it's better, but I don't know which name was better for part 1. Because having them have, like, clearly understandable names is maybe better than them having names that reflect the input. I guess best of all, in an ideal world, would be to have them be x1 and 0 when you parse them, and then do a transformation step where you convert these to, like, internal domain types, pass, set, and clear, or something like that, right? But no one's going to put that much effort into Advent code, so I think choosing a meaningful name over a name that matches the input was a reasonable choice, even though we did have to back it out. And apply floating, I think, was kind of nice. Oh, I guess we could rewrite it to not use the let in anymore. Oh, also we could get rid of this type. I don't remember why I put it in there. Yeah, let's make a couple changes here before we're done. Oh, just because I wanted to tell you that what I had was a list of int. I just wrote that down for expository reasons. I mean, the word, at the very least, we could turn this into a where, which is like a little bit nicer, I think. Well, this where. Map sum of sequence bits. Yeah. This seems pretty good, I think. Okay. I don't think there's anything else going on that I wanted to roll back. Nah, I'm good. Okay, that's all for today. Hope you guys enjoyed. Thanks for watching, and I'll see you next time.